Look at this. Beautiful control. I mean, they want, where it's over here, 61 degrees, something like that. And it's right on. Beautiful, huh?
It's pretty sweet.
Huh?
It's pretty sweet.
Y'all see the same thing? Y'all see the same thing? What do you go, what if you ask for 45, Ronnie? It can't get there. The fan can't cool it down to 45, so he's in his operating range. How come it doesn't oscillate like some of you other people? It goes bananas until he gets 130 negative control again.
Did it take so much longer for your system to respond?
Do you remember what his dead time was? Anybody remember what the dead time for this system is?
Near zero.
Huh?
0.
Not 0, it's 0.01 or something like that. I don't remember what number it is. And his tau,
It's big.
about 10 times that. If your dead time is a whole lot bigger than your time constant, tau, is a whole lot bigger than your dead time is what kills you. He has very small dead time. All these people in here. Sweet, huh? So, that's why he gets very close to a set point. If there's any error there, it's hard to see. Let me see, steady state error. That's one thing. By the way, why didn't he change his set point? When did he change his set point from 52 to 61? Why didn't he do it back here? Why didn't he change the set point earlier?
You would get steady state.
Because the only meaningful, useful data is if it has reached steady state, and then you change the set point. This is garbage. You shouldn't even have shown us this. Question? Yes, sir.
So is it have anything to do with equipment, or is it just the fact that we're dealing with temperature versus pressure? Like the response of the system.
The response, does it have anything to do with the equipment? Well,
Is it the equipment you're using to measure, or is it just what you're measuring? Like on the pressure system, that's all over the place.
What's all over the place?
Our plots. It's very noisy.
True, it's very noisy. And what's the ratio of dead time divided by time constant for your system? This?
It's not.
Let's go back to where you have your dead time and your time constant. Okay, here's some dead times. Notice there's 0.04, that's pretty small. This is what in units, minutes. Whereas the time constant is 10 times larger. My guess is all of the other systems have about the same time constant and dead time. Ballpark.
Mine was both 0.1.
Say it again?
Mine was both 0.1 second. It was
Your
almost the same.
dead time and time constant were both 0.1. They're about the same order.
Yeah.
So you don't get as nice, easy to control stuff. Yours goes bananas. Because by the time the time constant, once it gets up to somewhere, it goes back down.
But is there a reasoning for that? Is this system going to be different? Like our most temperature-based system is going to be easier to control than a pressure system?
It depends on where you measure the temperature. Is it okay if I draw on the whiteboard just for a little bit? Oh, I'll tell you what, I'll do something better. What color are you now?
Same.
Huh?
Same.
Do I have a salmon? Okay. Let's do salmon. He's changing the flow rate of the cooling air by the changing the percent of the input to the fan. Faster, higher input to the percentage input to the fan, the faster it turns and faster it flows. The measurement is made immediately right there. That tells you when the heat goes up, the temperature measures it immediately. Now, he's got something that comes over here. What if he measures it over here? This is measurement one. This is measurement two. It would take longer for that measurement two to notice what the temperature is. It's called transport lag. So it's not a very wise thing to measure the temperature somewhere else, unless this is where the important temperature is. You make a measurement wherever it's important to you in your process. The closer the heater is to where you need that, the better control you get. Does that make any sense? You can eliminate transport lag, the whole system will work better. Or minimize.
I was just thinking, well, we're working on a project in the experimentation where we're measuring pressure, and the Kistler device measuring that is very noisy. And it seems that our pressure system is very noisy also. And I was just curious if that was typical of pressure type systems.
Typical of pressure type systems.
And like the temperature systems, are they going to normally be a little more well behaved?
Yeah, that's probably overgeneralization, but we'll take it.
Okay.
Any questions on that? Now, turn on the, let's go back to here. These people hardly even need any better controller than this. Pretty nice here, a little bit of offset. It's pretty nice here. But if you have a picky customer, this might not be good enough, so you might have to add the integral term, which I haven't told you this. Shall I tell you this? Adding the integral term always gets you what you want. Always gets you what you want. Proportional has an offset. Integral term has a zero offset. Always, always, always. Shall I say that another time? Yes. Always, always, always. Proportional integral gives you zero offset. Gives you exactly what you want. You suppose there's any ifs that I'm hiding from you? Because if you put the wrong parameters in case of C still has an ultimate, so if you go higher than that, you're going to get oscillations. Like, go a couple slides forward. They put in, oh, there you go. You can even get this with proportional interval if you're, well, I hate to say this. How shall I say it? If you made a mistake, then put in, let's say you wanted -13 and you actually put in -130, this is what you're gonna get. So you can, proportional integral can cause you to have this kind of behavior if you make a mistake. So don't ever make a mistake in between your controllers, okay? All right, so thank you, Stewart. Next.
Everybody, my name is Miriam Deverne. I'm going to present the makeup of the week 12 for the Ivory team. My teammates are Resul and Justin Hobbs. So the outline of this presentation are going to be the system description, then the results of the model of the root locus, the model of the proportional only controller, and the experimental values, and a brief conclusion. This is our system. It's a absorber water flow system, and this is a picture of the Coriolis flow meter. So for the root locus on the flow region from 0 to 4 liter per minute, we can see on the plot the different decay ratio from critical damping until the KCU value, which is an ultimate value of the controller. This is for the highest region of our system, so 8 until 12 liter per minute. Same graph with a little bit of different values on the graph. So this is the values that we found for 2 regions. We can see that the values for the lowest regions are bigger, the controller is bigger. The ultimate value is reaching 19 person per liter per minute per person, while it's 14 for the highest region. This is a comparison between the 2 regions. So on the graph, we can see that the lowest region is a little bit higher in output. This is for the quarter decay controller. It's the same as the critical decay. And for the ultimate value, the gain controller needs to be 19% to never settle down, while it needs